Chapter 1 Carbanion Lecture number 3. In our class Organic Chemistry, we start with Wittig reaction. So, is related with the preparation of alkene. So, alkene, the olefins, the second name for the alkene, can be prepared from the reaction of phosphonium yield with aldehyde or ketone. So this is the phosphonium yield. It will be reacted aldehyde or ketone to give an alkene as main product, also with R3P oxygen as side product. If you look to these two molecules, you have to remove this from the middle and bond directly this carbon with double bond. You have to cancel this spark as a short note for you. So how the phosphine yield will be prepared and how the reaction will be happen, just we take a few example here. Look to this aldehyde and this phosphine yield. So it will be this part from the phosphine yield, it will be removed with the oxygen. And we have carbon double bond directly with the CH2, it will be give you the product. The same thing here. This part, it will be removed with the oxygen and carbon double bond CH3. This part, the oxygen, it will be removed with the this part from the phosphine yield. So it will be carbon double bond carbon CH3. This is the product. The Wittig reagent is an organophosphorus reagent. It's called Wittig reagent. So this is the Wittig phosphine yield. A typical Wittig reagent has a phosphorus atom bonded to 3 phenyl groups, this phosphorus and this phenyl group, and another alkyl group that bears a negative charge. This alkyl group that has a negative charge. Okay? As abbreviated طبعا can be repeated again or write it again in this figure. The phenyl, pH, phenyl by 3, P carbon minus, and we have two resonance structure for this yield. We have this and we have this. It will be make a double bond here to give you the second resonance structure. Wittig reagents are synthesized by two-step procedure. So we start from a triphenyl phosphine. It will be react with alkyl halide. And during SN2 reaction, the mechanism for the reaction by SN2 to give you phosphonium salt. Secondly, phosphonium salt, we have loss a proton. It will be loss a proton to give you the yield. So the base used to remove a proton from the phosphonium salt, typically stronger base. It will be strong base, like butyl lithium. This base can remove this proton to produce the phosphonium yield. So this is called Wittig reagent. Secondly, the Wittig reagent, it will be this Wittig reagent, it will be react with the aldehyde or ketone. طبعا the mechanism is nucleophilic addition from 4 member rings. It will be give you intermediate as 4 member rings intermediate. And secondly, this intermediate enter to the elimination reaction to produce the alkene and triphenyl phosphonium oxide as side product. Not an advantage of Wittig reaction over elimination method used to synthesize the alkene that you always know the location of the double bond. Okay, by using Wittig reaction, always give a single constitutional isomer. So there is no multiple product, there is no side product here. just one product. There is no major or minor product here. So for this example, if we want to prepare this alkene from the cyclohexane, there are two methods to prepare the alkene from the cyclohexane. One of them is during a Grignard reagent. So the Grignard reagent will be added to the carbonyl to produce alcohol, tertiary alcohol. So tertiary alcohol react with H2SO4 to enter to the elimination reaction to produce alkene. So there is two possibility for the product. Maybe the double bond it will be here, maybe the double bond it will be here to give two product, major product and minor product. But by using phosphonium yield Wittig reagent, just one product it will be formed in this reaction. So this very advantage to Wittig reagent. So this what has mean here. It just give you single constitutional isomer. The next subject we have to talk about it in this lecture is the carbanions as nucleophiles in nucleophilic acyl substitution of ester and acidic chloride. Ester and acidic chloride. So the first reaction here is the Claisen ester condensation, formation of beta keto ester from the carboxylate ester. So this esters it will be react with each other to produce beta keto. This carbonyl for the ester, alpha carbon, beta carbon. Carboxylic ester, the ester compound that have alpha hydrogen can undergo, we have alpha hydrogen, condensation reaction upon a treatment with strong base to yield beta keto ester. This reaction is called Claisen ester condensation. It is a Claisen ester condensation, or some books they call it acetoacetic ester condensation. The corresponding intramolecular reaction is called Dieckmann condensation. Okay, if we have intra reaction between compound that has two functional group of ester to the end like that, like this product. So this it will be enter carbanion here, and this carbanion will be add to this extra to this ester, and this will be removed. This is called Dieckmann condensation. It is intra reactions of the Claisen ester condensation. So reaction mechanism here. Firstly, we have to use base to remove alpha proton to produce carbanion. This carbanion is stable by resonance structure. Secondly, the carbanion will be added to the carbonyl of the second molecule of the ester to produce this intermediate. Now we have negative on the oxygen, make double bond, OR as leaving group. It will be leave the structure as alcohol or as a base. So it will be give you beta hydroxy ester. The same thing here. This compound it will be react with itself to produce this product. Carbanion will be add, and then this it will be leaving group. Leave the structure to give you the product. So the mechanism is the mechanism. For Dieckmann condensation mechanism, the same thing. Firstly, produce carbanion from here or from nothing, no different. From here, carbanion. This carbanion attack the carbonyl for the second functional group to give you a 5-member ring cycle. So this is the leaving group. This negative charge make double bond, and the leaving group leave the structure. Across Claisen condensation here, and base promoted carbon-carbon bond forming reaction between two different ester. The ester that we use, they are two different ester. In this case, we call it a crossed Claisen condensation, or an ester and another carbonyl compound. Okay, an ester, one of them ester, and the second it is not ester compound to produce beta dicarbonyl compound. So to avoid complex mixture for of to the products, this reaction is most efficient when one reactant lacks alpha hydrogen. So if one of the reactant molecule without alpha hydrogen, it is better to prevent the multi-products. Example, ester of benzoic acid and formic acid. So the benzoic acid here and formic acid, and serve only as here. Look, this here. This ester without alpha hydrogen. 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 So like here ethyl benzoate, and this ester compound. Here we don't have alpha hydrogen. So the carbanion it will be produced from this compound. Carbanion and carbanion attack the second molecule to give you the product, to give you beta hydroxy ester. This compound with this reactions, also this has alpha hydrogen and this without alpha hydrogen to give you this product. Again here what we have, this both of them have alpha hydrogen. This is normal reaction, Claisen reaction, normal reaction. So this is normal Claisen reaction. This is the cross. This about crossed Claisen condensation. What about mixed Claisen condensation? Another type of cross Claisen condensation occur when ketone is react with ester. This is the second case we talked about it. Ester with not ester compound, with another carbonyl compound. It is called mixed Claisen condensation. So the use of an ester without alpha hydrogen is not necessary due to the greater reactivity of the ketone. So if the ketone and the ester, both of them has alpha hydrogen, no problem. No problem in this case. Why? Because the greater reactivity of the ketone. So the alpha hydrogen of the ketone are much more acidic than those in the ester. So the pKa for the ketone 20, pKa for the ester 25. So the base always remove a proton from the ketone. Remove a proton from the ketone. The alpha hydrogen of ketone will be preferably deprotonated. Okay, the base remove proton from the ester to make it enolate Claisen donor. It will be carbanion. So the ester will be therefore be electrophilic Claisen acceptor and is all likewise commonly used in large X here. The beta diketone Claisen product can be طبعا here irreversible deprotonated to the more acidic alpha hydrogen, make it the reaction main product. So example for mixed, look, this ketone, this ester, this mixed Claisen condensation. So always if you have a base, the base it will be remove this proton from here, and so the carbanion it will be add to here, and this it will be leave the structure to give you the product, the same thing here. This ketone, this is aldol reaction, ketone, and this is aldol reaction. This reactions is aldol reaction. So the core reaction, another reaction here is the core reaction here, the Gilman reagent coupling of lithium dialkyl cuprate with acid chloride. With acid chloride. So here lithium dialkyl cuprate, it is like green reagent. It is like also green reagent. This reaction often referred to as the Gilman reagent coupling is a powerhouse in organic synthesis. It always to transform an acid chloride into a ketone. We convert the acid chloride to the ketone without overreaction of the ketone. Often is found with other organometallic reagent. He mean here like a green reagent. When you react lithium dialkyl cuprate, this also known as Gilman reagent, with an acid chloride, this is the acid chloride, the alkyl group are replace the chlorine atom. So one of the alkyl group here, negatively charged carbanion, it will be attack, and this chlor, it will be leave the structure to give you the ketone. So the ketone cannot be further react with the Gilman reagent as in the Grignard reagent. So if you have ketone and the ketone the ketone react with the Grignard reagent, so the reaction will be happened and give you alcohol. But here the ketone cannot be further go to the alcohol. So here, if you have ketone and you react the ketone with Gilman reagent, there is no reaction. Can be. So example, here we have acidic chloride. This is the acidic chloride. It will be react with the Gilman reagent. This is the butyl. It will be substituted here, and the chlor, it will be removed. Look, it will be give you this product. This also acidic chloride, it will be react with this phenyl by 2 cu lithium, and for this example the phenyl, it will be substituted here. This here we have carbon. It will be substituted instead of the chlor. The chlor, it will be removed, and this, it will be added to here to give you this product. Why you use Gilman reagent again? The real beauty of this reaction is the selectivity. If you use the Grignard reagent or an organolithium reagent, you will be don't stop to the ketone. The ketone will be go to react further. Those reagents are so hot, yani strong reagent, nucleophile, that they will immediately attack the ketone again and to give you another compound. So to give you the tertiary alcohol. Again, look here, ketone. With the Grignard reagent, the ketone can be further go to give you tertiary alcohol. But with the Gilman reagent, no. The ketone, it will be don't react with this reagent, and it will be stopped to the ketone. So it is a mild reagent, not like Grignard. Grignard is strong, so strong. So the mechanism here, nucleophilic attack, and this, it will be open, minus on the oxygen, make double bond, pi bond, and this leave the structure to give you the product. Easy mechanism, 2-step, nothing else. Another subject here, carbanions as nucleophile in SN2 reactions with alkyl halide. Also here, the first reactions we will talk about it is Corey-House synthesis. Corey-House synthesis is a powerful organic reaction used to synthesize complex طبعا high yield alkane. It used to join two different alkyl group together. And these reactions, alkyl halide react with lithium dialkyl cuprate. This is the lithium dialkyl cuprate. It will be react with alkyl halide. طبعا the mechanism that is the SN2 mechanism, because this is carbanion and nucleophile. It will be add to this alkyl group, and this, it will be leave the structure to give you complex alkane with big structure. So lithium dialkyl cuprate, it will be known as Gilman reagent. It will be can be synthesized by using reaction of alkyl halide with the lithium to give you alkyl lithium. Secondly, alkyl lithium, it will be react with copper iodide to give you Gilman reagent. And now Gilman reagent is ready to react with the alkyl halide to produce the carbon-carbon new bond. So this is the Gilman reagent It will be react with alkyl halide to produce more bigger structure or more complex organic compound. The primary significance of this reaction is that it can be used to prepare symmetrical or unsymmetrical stride chain of the hydrocarbon and the branch chain of the alkane. So this alkane can be symmetrical or cannot be symmetrical can be prepared by using this method. It is powerful and practical tools for synthesis a complex organic compound. Complex organic compounds mean compounds with high molecular weight. Second reaction here is the metal acetylide synthesis of the alkyne. So you know the alkyne has always acidic hydrogen. So this acidic hydrogen can be removed by base to give you carbanion on the carbon, and this carbanion can be react with alkyl halide to produce the alkyne compound. So this here called metal acetylide, and the product it will be alkyne. So this another example here. Also this it will be add to here, and this leave structure to give you carbon. Okay. Also here the reactions can be react with the epoxide. This carbanion it will be attacked from this side. This side it is less steric effect, not this carbon. So when attack this it will be open, and finally the negative can be take a proton to give OH to give you alcohol here, and the alkyne, the main part of the alkyne. So terminal alkyne, as I told you before, that have acidic proton because the sp hybrazide. So it is always more acid. Alkyne is more acid than alkene or alkane. What he write it here? Notice that secondary alkyl halide. This secondary alkyl halide are not the best option for this type of substitution. Why? Because the elimination can be happened. So, for example, if you look to this reaction, carbanion cannot be attacked from here to remove the halogen. So it's easier for this carbanion to remove the alpha proton and produce alkene. This is the problem with the secondary alkyl halide. So the secondary halide that we use in this reaction must be primary because the mechanism is SN2 mechanism. So in this reactions, the carbanion here it will be work as base, not nucleophile. It will be react as base to remove the alpha, beta carbon, beta proton from here and to produce alkene. This examples try to resolve this example. It is like homework for you. So another reactions also is the malonic ester synthesis. So the malonic ester synthesis is a classic organic chemistry method used to grade substituted carboxylic acid. It's allows you can take simple building blocking diethyl مثلا for example malonate, diethyl malonate, and grow the alkyl chain onto this compound. So eventually transforming it to the functional of the acid. So for example, look, this is the alkylation. The alkylation, of course, the alkylation of malonic acid here, the alkylation of malonic acid is easy. By using base, the base remove alpha proton, this is the acidic proton, and the carbanion attack the alkyl halide to produce carbon-carbon new bond. So the same thing here, bi-base carbanion. So it will be react with alkyl halide. Finally, this compound can be entered to the decarboxylation with heating to remove the or to cancel one of the carboxylic acid groups to the hydrogen, and it will be produce CO2 gas, carbon dioxide as side product to give you the new carboxylic acid compound. So again, from here, if you look at to grade substituted carboxylic acid. So this is the substituted carboxylic acid. So the reaction mechanism here is the base remove a proton, the acidic proton, give you carbanion. طبعا carbanion is stable by resonance with twice carbonyl from here. Finally, the carbanion attack the alkyl halide to give you the product. So if you look by base Br, it will be remove. That meaning we have CH2, CH3, CH2, CH3 here. This is the product. By another base, because we have also remaining alpha proton, also it will be removed and react with alkyl halide to give the product. This product can be entered to the decarboxylation. The same thing here. The carbanion from here can be to the if you have this alkyl halide, this carbanion can be attacked here, and this remove it to produce this structure, this compound. So again, if you have two alkyl halide, yani one molecules that has two end with the alkyl halide, so it can be also give you cyclic compound with the base in the basic medium. Base mean we have to use base here. So the synthetic importance of malonic ester synthesis follow from the fact that substituted malonic ester can easily be hydrolyzed, okay, and subsequently decarboxylation to yield substituted acetic acid. This is the main point here. Substituted acetic acid. This route to substituted acetic acid is an important method in organic synthesis. Okay, so if you look here, by using diluted acid or base, so it will be ester can be hydrolyzed to carboxylic acid. So the carboxylic acid can be entered to the decarboxylation to give you carboxylic acid derivative. Okay, so one of them, this or this, it will be leave this structure. For example, this it will be work as leaving group, leave this structure. So by using base, we have carbanion with alkyl halide. It will be give you carbon, say 3 carbon atom, carbon, like that. So another proton can be removed, give you CH3. It will be give you also CH3 here. Hydrolysis and heating decarboxylation, this it will be cancelled as cancelled from the structure to produce this product. Okay, try to write all the step alone. Write the product for step 1, product for step 2, product for step 3, product for step 4, like that. Okay, alone. Go to the final product, this kind of product. So the fundamental process of the malonic ester synthesis again to convert the alkyl halide into carboxylic acid. We convert the alkyl halide to the carboxylic acid while adding 2 carbon atom to the chain. We have to do a carbon atom to the chain. Think of it has reliable way to grow specific type molecules, substituted acetic acid. If you have alkyl group and you want to turn out to the RCH2COOH. So if you have alkyl group and you want to convert the alkyl group to carboxylic acid derivative with additional carbon atom. With additional carbon atom. So the second, the another reaction here is the acetoacetate synthesis of ketone. So it's also called acetoacetic ester synthesis. Is the classical organic chemistry method use grade alpha substituted acetone methyl ketone. It is essentially a way to take a simple building block ethyl acetoacetate and decorate, يعني it will be designed. You can design it, okay? And with what? With alkyl group before stripping away from unnecessary ester part. So if you look to this, now this is beta keto ester. The beta keto ester can be entered to the convert to the carbanion. So carbanion react with alkyl halide, hydrolysis, and then hydrolysis. So the ester it will be converted to the carboxylic acid group. So carboxylic acid group can be removed from the structure by using decarboxylation heating to give you ketone, to give you the ketone. So it is an important reaction to prepare the ketone compound by using this type of reaction to prepare the desired the wanted ketone compound. One of the important method to prepare the substituted ketone. طبعا يعني symmetrical ketone or unsymmetrical ketone, both of them. So the process with the ethyl acetoacetate, the magic lies in the alpha carbon here between two carbonyl group because it's flanked between two electron withdrawing group. Yes, this is acidic. He mean here the proton is acidic proton. The synthesis typically follows this four stage: deprotonation, or alkylation, or hydrolysis, and decarboxylation. This is the main steps in this synthesis to convert or to produce the ketone compound. Okay, to produce the ketone compound. So it is four step. Deprotonation, this is the deprotonation, and alkylation, this is the alkylation, hydrolysis, this is the hydrolysis, and decarboxylation, this is the decarboxylation. Note here why use this reaction instead of direct alkylation. Okay, can be used direct alkylation or not. So if you try to alkylate the acetone directly with the base like methane NaOH, so you should get a mix of self-condensation aldol product and multiple alkylation. So by using acetoacetic ester will provide control and high yield because the middle carbon is so much more reactive than other. So if you used ketones here and you want to make for the ketone alkylation, you will be has aldol condensation or aldol product, and you will be has multi products. Okay, multi products, and it will be give you problem here. Maybe it will be get multi alkylation. It will be multiple alkylation here. Also can be happen. Multiple alkylation can be happen. So this method, it is a good method to prepare the ketone without any problems, without any polyalkylation, without any self-coupling for the product, for the reactant, for the starting material. Okay. So this is the benefit of the acetoacetate synthesis of ketone. Another type of reactions can be طبعا included with carbanion is the addition to an alpha beta unsaturated carbonyl compound. And when we talk about alpha beta unsaturated compound, when we talk about this compound, directly you have to think about important reaction called Michael reaction. Michael reaction is so important reaction in organic chemistry. So also give you carbon-carbon U bond.